The purpose of this short exercise is to actually run through the process of calculating the gradient for a scalar function. In this case, we'll just use the letter h to represent that. And to do the worst case scenario, we'll do this in spherical coordinates. Let's define h as z r sine theta cosine phi. So it's in spherical coordinates, and we'll carry on. To calculate the gradient, the main thing is to just keep your head straight as you go through the equation. Compared to doing the divergence, it's not necessarily uglier, so you just have to take your time doing the derivative and make sure you don't mess up. So in the case of the r direction, you just take the derivative with respect to r. In respect to my own handwriting, this doesn't make sense to have a z here. After taking a closer look, this should be a 3. So d by dr, 3r sine theta cosine phi, and that will give you the r hat component. The case of theta, you have to divide it by r. It's r d by d theta, and then our function again, 3r sine theta cosine phi, and this gives us the component in the theta direction. And then in the phi direction, you have to divide by 1 over sine phi. And d by d phi of 3r sine theta cosine phi in the phi hat direction. As is the case with taking the divergence in the cylindrical and spherical coordinates, the main thing to keep in mind is just in the case of divergence, you might have some function, you might have some things that you have to multiply on the right-hand side of the derivative operator and some terms on the left-hand side. The key thing is to make sure you keep this straight. In this case, all of the normalization terms are on the left side of the differential operator, so just make sure that you don't take those into account when you're taking the derivative. Once you have that set up, you can then just go ahead and take the derivative with respect to the variable in question. So in this case, if you take the derivative with respect to r, the r goes away, so you're left with the d by dr is equal to 1, so then you're left with 3 sine theta cosine phi of r hat, plus, in this case, if you're taking the derivative with respect to theta, the sine theta turns into cosine theta. So you have 3r cosine theta cosine phi, and then since the r is constant, you can actually just go ahead and cancel these. When you're taking the derivative with respect to theta, you can pull the r out, so these cancel, which leaves you with 3 cosine theta cosine phi in the theta direction. The same thing applies here. Since this is a derivative with respect to phi, the r is a constant for the purposes of this derivative. Therefore, you can do this cancellation here, and you're left with 3 sine theta cosine phi. If the derivative with respect to phi gives you minus sine phi, therefore you have 1 over sine phi 3 sine theta sine phi with a negative sign from the differential operator. This cancels out, gives you the answer in the phi direction. Cleaning that up, we'll just copy everything in the previous line here. Looks like I had a little pen hiccup there. So I was at cosine phi in the r hat direction. So far I'm just copying everything in the previous line, but in this case this cancels out, the minus sign comes out. You have minus 3 sine phi in the phi hat direction. So that is your final answer. The one other thing to point out is the fact that this is a scalar field. So you're plugging in the same scalar field in all 3 directions, and when you take the derivative, each of these components have a basis vector or unit vector associated with them. So then the output is actually a function, is actually a vector function, where now if you put in r's, in this case r's had all canceled out, or thetas or phis, now what you get out is a vector instead of a scalar value. So again, the concept of a gradient, the notation is just gradient h, or del h, and the main thing to remember is that you put in a scalar function, and then out comes a vector function. And going back to the analogy, just to reiterate, to really drive home the point, the analogy that makes the most sense to me is if you have an isoplane and the altitude maps that you have, if you view that as a potential, the gradient gives you vectors that tell you how steep the uphill is. So the gradient points to the most uphill direction, and the magnitude tells you how steep that particular location is. And there you have it, the gradient.